For any assignment-related queries, call us at +1 678 648 4277. You can mail us at info@eduassignmenthelp.com or reach us at https://eduassignmenthelp.com. For any assignment-related queries, call us at +1 678 648 4277. You can mail us at info@eduassignmenthelp.com or reach us at https://eduassignmenthelp.com. Problem 1. Revised BCJR, some product, decoding of SPC codes, as shown in Problem 6.4 or Figure 1 of Chapter 10, any, NN-1-2, single parity check code has a two-state trellis diagram. Consider the 872 code, and let the received sequence from a discrete time AWGN channel with input alphabet, ±1, and noise variance 2 is equal to 1 be given by R SAD phase 0.1, -1.0, -0.7, 0.8, 1.1, 0.3, -0.9, 0.5. Perform BCJR, some product, decoding of this sequence to determine the app vector for each symbol YK. Hint: the special algorithm given in Section 13.5.2, see Problem 9.5, to implement the sum product update rule for zero-sum nodes may be helpful here. Compare the complexity of BCJR decoding to Viterbi algorithm decoding. Solution: first, let us draw the normal graph of a minimal trellis realization of the 872 code. This graph is shown abstractly below. Moreover, it is easy to see that the 3-2 branch constraint codes are all 3-2-2 zero-sum codes, and the 2-1 codes are simple repetition codes that need not actually be shown. Therefore, the trellis realization may be drawn simply as follows. eduassignmenthelp.com. Note that this trellis realization of the 872 code is another cycle-free realization that uses 6-3-2-2 zero-sum constraints, as in the reduced HT realization of Problem 8.1. However, the diameter of this realization is 5, which is as large as it could possibly be. For a binary input Gaussian noise channel with inputs ±1 and Gaussian conditional probability density P, R, Y, SAD phase 2 pi sigma, -1/2 exp minus, R minus Y, 2/2 sigma 2, the a posteriori probability, EP of Y, ±1, given a received value R is, by Bayes' rule. Here sigma 2 equals 1, so SNR equals 1, 0 dB, i.e., the channel is very noisy. The two values P, plus or minus 1 RK, form the intrinsic information message iota K equals P0K, P1K, derived from each received symbol RK 0 less than or equal to K less than or equal to 7. These values are computed from the received vector R SAD phase 0.1, -1.0, -0.7, 0.8, 1.1, 0.3, -0.9, 0.5, in the following table. Note that it would have sufficed to use the unnormalized pair, ERK/sigma 2 E minus RK /sigma 2. We also compute the Hadamard transform, P0K plus P1K equals 1, P0K minus P1K equals IK, of each pair of values for later use. eduassignmenthelp.com. RKP0K P1K IK. R0 equals plus 0.10, 0.55, 0.451 plus 0.10, R1 equals minus 1.00, 0.12, 0.881 minus 0.76, R2 equals minus 0.70, 0.20, 0.801 minus 0.60, R3 equals plus 0.80, 0.83, 0.171 plus 0.66, R4 equals plus 1.10, 0.90. 0.101 plus 0.80 R5 equals plus 0.30.65 0.351 plus 0.30 R6 equals minus 0.90.14 0.861 minus 0.72 R7 equals plus 0.50.73 0.371 plus 0.46. Note that IC equals tan RK slash sigma 2, so IC is almost equal to RK slash sigma 2 for small RK. The sign of IC represents a hard decision, whereas the magnitude 0 less than or equal to IC less than or equal to 1 represents the reliability of that decision. We then propagate the app messages through the graph below, using the BCJR, sum product, algorithm. Note that in the forward direction alpha 1 equals iota 0, alpha k is the sum product update of alpha k minus 1 and iota k minus 1 for 2 less than or equal to k less than or equal to 7, and finally epsilon 7 equals alpha 7. Similarly, in the backward direction, beta 7 equals iota 7, beta k is the sum product update of beta k plus 1 and iota k for 6 greater than or equal to k greater than or equal to 1, and finally 0 equals beta 1. Think is the sum product update of alpha k and beta k plus 1 for 1 less than or equal to k less than or equal to 6. eduassignmenthelp.com 4a, 3u2, constraint code CK, the set of past two tuples consistent with a 0 value for any incident variable is CK, 0, equals, 0, 0, 11, and similarly CK, 1, equals, 0, 1, 10. Therefore the sum product update rule is where Pj and Pj are the two pasts upstream of P. Alternatively, following the hint, we may use the special rule for zero-sum nodes to obtain the Hadamard transform of P0, R, P, P1, R, P, simply by component-wise multiplication of the Hadamard transforms of P0, R, Pj, P1, R, Pj, and P0, R, Pj, P1, R, Pj. By either method, we obtain the following values for the forward messages alpha k equals alpha 0k, alpha 1k, and their Hadamard transforms, alpha 0k plus alpha 1k equals 1, alpha 0k minus alpha 1k equals ak, the backward messages beta k equals beta 0k, beta 1k, and their Hadamard transforms, 1 bk. And the extrinsic information messages epsilon k equals epsilon 0k, epsilon 1k, and their Hadamard transforms, 1 ek. eduassignmenthelp.com alpha k, alpha 0k, alpha 1k, ak alpha 1 equals iota 0.55 0.451 plus 0.10 alpha 2 0.46 0.541 minus 0.08 alpha 3 0.525 0.4751 plus 0.05 alpha 4 0.515 0.4851 plus 0.03 alpha 5 0.51 0.491 plus 0.02 alpha 6 0.5035 0.49651 plus 0.007 alpha 7 0.4975 0.50251 minus 0.005 SSK SS0K SS1K BK SS7 equals iota 7 0.73 0.271 plus 0.46 SS6 0.335 0.6651 minus 0.33 SS5 0.45 0.551 plus 0.10 SS4 0.46 0.541 plus 0.08 SS3 0.475 0.5251 plus 0.05 SS2 0.515 0.4851 plus 0.03 SS1 0.49 0.511 minus 0.02. eduassignmenthelp.com Notice how the reliability of the forward and backward app messages alpha k and beta k degenerates as more and more intrinsic information messages iota k are incorporated into them. The app vectors p yk equals 0 r, p yk equals 1 r, For the symbol variables yk are ultimately obtained by component-wise multiplication of iota k and epsilon k, normalized. We note that for all k,